but we do have material we have to cover, unfortunately. You cannot minimize while you were recording. Okay, whatever. Oh, you know what? I didn't open the questions because I was distracted. All right, which one do I want to do first? Let's see. Oh, this is a good one. All right, so let's start with this. Yes. And let me get the polls going. Boom. I mean, more like in office hours, people are gonna, ask a ton of questions, I'm sure, about some of the stuff that we've been learning. So, yeah. But no, we have to cover the material that we're going to cover first. This is a long question. This question does take a little bit of time, so take it slow, parse it out.
Nope.
And for the record, this was a term test question 1 year.
It was. I was about to say I really like this question because it looks simple at first, but it has a couple of extra components to it.
Mm-hmm. Yeah, I think when it was term test that we scaffolded it, there were a couple of parts to it, but
I remember it wasn't a very well answered question on the term test.
Okay, I'm going to give you a minute, one more minute, see what you can do. Set notation of pain. Why would that be true? I mean, maybe it's possible. It depends. And some, like anything, right? There can be like hard questions and easy questions and nasty questions. Okay, so this is an interesting distribution though here, right? So I will say, first of all, congratulations. You did better than last year. So last year, something like 80% of the class said B. And B is not the correct answer. So this year, only 43% of you said B, which was not the correct answer. And actually, a third of you said C, which is the correct answer. So you did better than last year. And really, that's what matters, right? Is that you beat the previous year. Okay, yeah, so the answer is C. The answer is 3/4, and let's think about why. And in fact, let's think about what the problem says, first of all. So this is a weird problem, right? So it says you roll a dice first, and then depending on what the die shows, that's how many times you flip a coin. So if you roll a 4, then you will flip 4 coins, right? So what the question though is asking, it says, what's the probability that x equals 6 given that y equals 5? And this is backwards than what we normally compute. It's saying, given that I know that 5 heads appeared, what is the probability that I rolled a 6, right? And you can imagine that the probability should be pretty high, because if you had 5 heads, if you flipped 5 heads, first of all, you had to have either have rolled a 5 or a 6, right? The only way you could even get 5 heads is if you at least flipped 5 coins, right? So the probability of x being equal to 6, given that y equals 5, should be a pretty high probability. Like it's probably more than half, right? And so that kind of immediately takes us down to C or D, just from an intuitive viewpoint. And that's the sort of thing that we can do from there. Now, of course, that doesn't do any good, especially if it's not a multiple choice question on a test, right? You actually need to figure out what the answer is. So how do we do this? Okay, so what we're going to do is use Bayes' theorem, right? So Bayes' theorem, let's just recall what Bayes' theorem says. So why is my pen not working? We were doing so well for so long. It's been like 2 weeks since my pen broke. And now it's broken today. Stupid pen. Okay, hopefully this will fix it. So Bayes' theorem. Yeah. Bayes' theorem says that the probability of F given E is equal to the probability of E given F times the probability of F divided by the probability of E. Okay, and this is really nice. This is basically, you use Bayes' theorem when you want to switch the order of the conditional probabilities, right? So what we're saying here is we want to determine the probability of F given E, and we're assuming that we know that the probability of E given F, right? And so in one of these events where you want to switch what the conditions are, Bayes' theorem is exactly the right way to do it. Okay, so that's the thing to look out for. When you're doing a conditional probability question, if it seems like we're computing the weird one, you probably want to use Bayes' theorem. Okay, so this is our goal here. So what we're going to do, so we've already got our events, right? Like X is basically the number that appears on the die, and Y is the number of heads that you flip. So we want to determine the probability that X equals 6 given Y equals 5. If we write that out using Bayes' theorem, that's the probability that y equals 5, given that x equals 6, times the probability that x equals 6, divided by the probability that y equals 5. Okay? Now, the conditional probability in here, okay, yeah, so I got a direct message saying, what do you mean by computing the weird one? How is it switched? How would you know? Okay, so let's think about this. So I claim that of these two things that I'm going to underline in blue here, so or maybe I'm going to overline them because that'll be easier. I claim that of these two things, this is the easy one to compute. Or maybe easier, not easy, but easier, and this is the harder one. Okay, because let's think about what this is saying. So this is the easier one. So this is saying, what is the probability that you had 5 heads if you flipped a coin 6 times? The probability of 5 heads in 6 flips, right? The other one though says if you got 5 heads, what's the probability that you flip the coin 6 times, right? And so that's what I mean by the weird one. Like if I said you flip a coin 6 times, what's the probability you get 5 heads? I think that for most of you, you're like, okay, that seems reasonable. Maybe even if I don't see how to do it immediately, I believe that that is a reasonable question to ask, right? You flip a coin 6 times, how many times? Like what's the probability you got 5 heads? The other direction is really weird, right? It's saying you know you got 5 heads, but you don't know how many times you flipped the coin. What's the probability that you flipped it 6 times? Do you know what I mean? So that's what I mean by weird one. Yeah, right. So that's the weird one. Okay, so someone tell me, what is the probability that y equals 5 given x equals 6? Now, even though this is a conditional probability question, we don't need conditional probability to solve this. This is the same thing as what I wrote down here. If you flip a coin 6 times, what's the probability of 5 heads? Can anyone tell me? Okay, let's try it this way. You flip a coin 6 times. What's the total? It's a fair coin. What is the total number of outcomes you could have? Oh, Jeremiah, very, very close. Agam, also very, very close. Okay, yeah, so Owen, exactly. So the answer is 2 to the 6, right? If you flip a coin, there are 2 to the power of 6, 64, right, Sean? Same thing. There are 64 possible outcomes, right? So if we flip a coin 6 times, there are 2 to the 6 equals 64 outcomes. Does everyone agree? Yeah. Right, because you've got 6 boxes, right? You're trying to figure out what are the options for the first row, the first coin flip, heads or tails. Second coin flip, heads or tails. Second coin flip, heads or tails. So that's 2 times 2 times 2 times 2 times 2. You do that 6 times, you get 2 to the power of 6. That's 64. So of those 64 flips, how many of them have exactly 5 heads? Yeah, Owen. Yeah, that's exactly right. So the answer is 6 choose 5, or equivalently 6 choose 1, or equivalently 6. So of those 64, 6 choose 5 equals 6 choose 1 equals 6 of them have exactly 5 heads. Okay, now do we see why? Let's double check this and make sure, because this is totally the sort of question that could come up on your term test, right? Where we say you flip a coin 6 times, what's the probability of 5 heads? This is totally a term testable question, right? So why is it 6? Can anyone explain why the option is 6 choose 5 or 6 choose 1 or 6? Yeah, okay, so I got, somebody, at least one person asking why it's true in a direct message. Can anyone explain? Does anyone have a valid justification for this? because we have 6 options and we need 5 heads, right? And Sean said we don't care about the order of them, right? Or we just need to choose the position of the heads, right? Like, let's put it like that. So we've got these 6 boxes, but exactly, your explanation is perfect. 3, 4, 5, 6. So these are our 6 coin flips. Yeah, exactly. We got to put the heads in 5 of the boxes. Yeah, 6 is the number of times that we flip, right? That's what x equals 6 means. It means you rolled a 6 on the die, and then the number that you roll on the die is the number of times you flip. So we could equivalently read x equals 6 as being the number of times you flip the coin, right? And yeah, Ariana, perfect. And Akansh, Ariana actually just answered your question. I'll do it more in a second. But Sean is exactly right. It's the number of ways of determining where your 5 heads are going to go, right? So you have 5 heads and 1 tails. So you need to place 5 heads in here. And there are 6 choose 5 ways of doing that, right? Alternatively, instead of placing 5 heads, what you could just do is say, let's figure out where the tails goes, right? Because you know that the other 5 have to be heads. So once you figure out where the tails goes, the heads are forced. So place 1 tails, that's 6 choose 1, right? And those are the same thing because the number of ways of placing the heads is the same as the number of ways of placing the tails, right? Yeah, okay, cool, nice. So Akansh, does that answer your question too? Like why those 2 things are equal? And then mathematically, if you write them both out, they're both 6 factorial or 5 factorial, 1 factorial. And of course, it doesn't matter which way, whether I write the 5 on the left or the 1 on the left, they end up being the same answer. But like conceptually, why are the same? Because placing heads is the same as placing tails. Okay, so this means that the probability that y equals 5 given x equals 6 is 6 divided by 64, right? And I'm just going to leave it like that. You could simplify it if you want. You could write it like 3 over 32. I'm going to leave it like that, and you'll see why in a second. Okay, so that's a probability that y equals 5 given x equals 6. Okay, and if we go back up to Bayes' theorem, great, that's this thing, right? So we've got that. What's the probability that x equals 6? On the term test? No, just explain one case. Yeah, exactly. Everyone, perfect. The probability that x equals 6 is, well, let's think about what that says. It says when you roll the die, what's the probability that you get a 6? Well, it's a fair die, so the probability is just 1 over 6, right? So this thing is 6 over 64. This thing is 1 over 6, right? Okay. So now the last thing that we have to do, which believe it or not is the hardest thing, is we need to figure out the probability that y equals 5. Okay, so what we need, maybe let me just kind of summarize that. So the probability that x equals 6 is just 1/6. Okay, so now we need the probability that y equals 5, i.e. the probability that we get exactly 5 heads. And we're not told how many times we flip the coin, right? We don't know how many coin flips have occurred. We're just saying, what is the total probability of getting exactly 5 heads? So how could I compute this? And I kind of gave it away. I said the answer. Okay, yeah, with different cases, Curdy, absolutely. Connie, that's going to be one of the answers. That's going to be part of one of the answers. I'd Agam, exactly, total probability. Gerper tap, that's, so we said there were 6 total ways, right? These numbers are all equal to 6. And so it's this divided by the total number of ways, right? And Owen, exactly, yeah. Oh, and you should totally send your messages to everyone because I think you've been right like every time. So, but exactly. So law of total probability. And you know, I got another message saying, look at the case when x equals 5 and x equals 6, and that's the same thing, right? So basically here, let me write this out like painfully long, just to make it clear what we're doing here. But I want to use the law of total probability. So what I want to do is I say, this is the probability that y equals 5 given x equals 1 times the probability that x equals 1, right? Plus the probability that y equals 5 given x equals 2 times the probability that x equals 2 plus dot, 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 plus the probability that y equals 5 given x equals 5 times the probability that x equals 5 plus, there's so many equal signs in this, right? Y equals 5 given x equals 6 times the probability that x equals 6, right? This is the law of total probability. What it's saying is we're going to compute the probability that we got 5 heads for every single possible way that we could have flipped coins, right? So we can flip 1 coin, 2 coins, 3 coins, 4 coins, 5 coins, or 6 coins. Those are our only options. And what we're going to do is say in each of those cases, what is the probability that I got 5 coins? Or 5 heads, sorry. Now, most of these are dumb, right? What is this probability right here? Well, it says it's the, exactly, Brandon, right? It says this is the probability that you got 5 heads when you flipped a coin once, right? And that probability is 0. I think you all agree, right? Like if I give you a single coin and I say, flip that coin, what's the probability that it came up heads 5 times? The answer is like none, right? There's absolutely no way that this could be true, right? And same thing, this is equal to 0, so on and so forth. So these are the only 2 that have a chance of not being equal to 0, right? So these ones are not 0. Okay, so we have to compute them. Now, we've already actually done, this one. Right? That's actually the numerator of Bayes' theorem, right? I'm going to scroll up in a second, but look at that thing I underlined in green and remember it's that when I scroll up, you're like, oh yeah, that is the numerator of Bayes' theorem. So the probability that y equals 5 given x equals 6 times the probability that x equals 6. Okay, remember that. I'm going to scroll up until we find Bayes' theorem. Oh, there it is. And yeah, look here. That's exactly the numerator, right? The probability that y equals 5 given x equals 6 times the probability that x equals 6. So we've already computed that. It's 6 over 64 times 1/6, right? So we've already did this one. It's 6 over 64 times 1/6. Okay, so we need this one. Okay, so we need to do the probability that y equals 5 given x equals 5. Now, that's pretty much exactly the same thing that we did above, right? When we were doing y equals 5 given x equals 6, but it changes just a little bit. And Connie, this is now where your answer comes in. What is the total number of ways that we can flip 5 coins? 32, right? Or 1 over 2 to the, or like 2 to the 5. And then how many of those 32 ways are exactly 5 heads? Ah, right. It's 5 choose 5, or that's the same thing as 1, right? Because think about it, Josefa, think about it. If you flip a coin 5 times, there's only one way they can all be heads, right? There's no other way that they could all be heads. There's only that one way, right? Is it has to be heads, 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 right? So there's only that one way. Okay, and then while we're here, what's the probability that x equals 5? 1 over 6, perfect. Okay, so now we've got all of the parts that we need, right? So by Bayes' theorem, so what do we have? So we have the probability x equals 6 given y equals 5. Let me just rewrite out Bayes' theorem so we can see it here. Y equals 5 given x equals 6 times the probability that x equals 6 divided by the probability that y equals 5. So this is going to be equal to 6 over 64 times 1/6 divided by 1 over 32 times 1/6 plus 6 over 64 times 1/6. Okay. Oh, okay. I got a direct message saying, why is it 1 over 32? So there's, let me maybe just kind of do this over here. So there's 2 to the 5 total possible ways of flipping 5 coins, right? That one's okay. It's the same reason why, right, when we were doing 6 coins, it was 2 to the 6. And now the question is, how many of those configurations look like this? Well, that's the only one, right? If you flip 5 coins for all of them to be heads, there's only one way of doing it. Or if you want, you can think of it as there's 5 choose 5 ways of placing the heads. There's 5 choose 0 ways of placing the tails. All those numbers end up being 1. Okay, and you can work out what this number is. If you didn't have, say, a calculator, the way I would do this is write everything as a power of 64 or a power of 6 times 64. So this is what, 2 divided by 6 times 64 plus 6 divided by 6 times 64, and then these all cancel. So you get 6 divided by 8, or 3/4. All right. So I got a direct message. X is the number that appears, or the amount. Okay, hold on. X. Okay, so X is the number that you got when you rolled the dice. When you rolled the die, that is the same as the number of times you flipped the coin, right? By the problem statement. Let me maybe go back to the problem statement. Okay, so you roll a d6. The X is the number that comes up, and then that's the number of coins you flip, right? So whatever the number comes up on the die, that's the number of coins you flip. So X is both of those things. It is both the number that comes up on the die and it's the number of coins that are flipped. Okay. And so you can see this is a little bit of work, but in practice, this is really the only way you're going to solve this problem, right? I mean, I guess if you really wanted to, you could write out all of the cases of, when X equals 1, X equals 2, X equals 3, X equals 4, X equals 5, X equals 6, write out all the possible configurations of heads and tails, but there's going to be like 150 of them. Make a chart, circle the ones where Y is equal to 5. But you can imagine that's a little bit of a mess, right? Even if you know that, for Y to be 5, X has to be either 5 or 6. Well, we just said there's 32 cases when X is equal to 5, and there's 64 cases when X is equal to 6. If we were to write all those out, that's 64 plus 32, which is what, 96? You'd have to write out 96 cases. Your chart would have 96 entries in it. Then you'd circle all the ones where Y is equal to 5, and then you'd look for the ones where X is equal to 6 in that, and you'd get your answer. But that's pretty messy, right? But if you really wanted to do it, you're free to try. Okay, does that make sense? It's a little bit long, it's a little bit hard, but every single application of Bayes' theorem basically follows that same model, right? Where you switch the conditional probability in the numerator, because you hope that's the easier one to compute. You work it out, you divide by that probability in the bottom. You almost always have to use the total probability in the denominator and expand it out like that. Yeah, and it's a bunch of things, right? You can imagine this is a great test question precisely because it tests a lot of different things, right? Conditional probability, your ability to even parse what a sentence says, total probability, and then counting, right? There's counting problem in here as well. So yeah, there's a lot of stuff in there. All right, what do I want to do next? We could do this. Yeah, I want to get an expected value problem in here. Some of these take a little bit long though, so I need to be very careful about which one I select. So I'm pretty much going to straight to 15. Yeah, let's do this one. Nice. I mean, that's phenomenal. I'm very happy if you guys thought that was fun. But Brandon, what does it cost you to buy a ticket? Right now, we're saying the ticket is free, right? But you can only have one.
That's a good logic.
Yeah, so what would happen in practice here, Brandon, is let's say that this was the scheme, right? You're playing the Lotto 6, You work for Lotto 349. And this is the scheme that you work out. What you would want to do is you'd want to figure out how should we price our tickets to ensure that we as a corporation, as the Lotto Corporation, make money. And whenever you get your answer, whatever your answer is here, you're going to set your ticket price to be higher than that, precisely to ensure that the expected value is negative. Right? And this is a fun thing because what you really want to do, especially if you're a jerk and you want to get people addicted, then what you do is you set your dollar, you set the price of your ticket to be as close to the expected value as possible, but still ensures, or not as close as possible, but close enough. But it still ensures that the expected value is negative, right? So for example, let's say that the answer is B, $18.30. What you would probably do is you'd set your ticket price to be $20. And so this way you have a negative expected value in that case, right? Your expected value is negative $1.70. But what you get when you make the ticket price close to the expected value is you start to screw with our pathetic human brains. And because what people will do, right, they have like great bias. When they win, they're exhilarated. And when they lose, they just kind of forget about it. So if you make the expected value close, or the ticket price close to the expected value, people will think that they're winning more than they're losing, when in reality, they're losing more on average. So when you look at almost any game in a casino.
Yeah, casino games is a great example of that.
Yeah. The expected value is like very small, but it's negative, right? So the expected value, like, you know, if you go to roulette, the expected value is very small, right? Obviously, it's going to depend on how much you bet, but the odds are against, like, even just playing on black and red, because there's 2 green suckers on a roulette thing, and that makes it less than 50% chance of getting red or black, right? So
47.4% precisely.
Yeah, there you go.
The table.
There you go. Yeah. So, right, when you look at the expected values, and thank God we've got Aziz in the background, you know, looking up the numbers. But we, when you look at the expected value of any casino game, it's almost zero, right? It's almost dead even to whatever you're betting, but it's always just slightly negative. And the casino is banking that in the long run, the law of large numbers takes an effect, and they will make significantly, and they do, right? We know casinos make a ton of money because people will lose on average more than they win, right? Casinos are all just math. It's all just mathematics, and making sure that you rig games so that people think they're winning, but in fact, they're always losing, right? And of course, I think we all know people who insist that they never lose at the casino, right? And as a general rule, that's not true, right? People think they never lose at the casino, but unless you're doing like a really good job tracking how much money you have, your brain, again, thinks it's winning, when in reality, in the long run, it's losing. And again, it's just a mathematical certainty that if you play games enough, you'll lose, especially games that are purely chance, right? Yeah, in some cases, absolutely. And because something like, you know, the odds start to change with things like blackjack, things like poker. And, you know, the house doesn't have a great interest in poker, but in blackjacks, there is some skill, right? And your skill can start to affect the numbers. But in something like roulette, the house cleans up because it's just chance every time, right? So Namir, you can answer that question yourself. You don't need me.
I agree.
Yeah. But okay, so here's the thing, Brandon, you know, like lottery tickets are entertaining. I think like we've all had fun. I remember getting like scratch tickets when I was a kid, and it's the sort of thing that like, it's just exhilarating because there's a chance that you win. And as long as you're not like banking on that, right? As long as you recognize that it's entertainment, I don't think there's anything wrong with that. The issue comes is if you're obviously banking on that sort of thing, you know, for your retirement, for example, then there's a problem. But if you just view it as entertainment, then I don't think there's anything wrong with that.
Mm-hmm.
There is a beautiful book, and let's say 1 minute for everyone else to do your final computations. There's a beautiful, maybe it wasn't a book. I don't remember what it was, but it was descriptive statistics and descriptive probability. And so, you know, you can compute the probability of winning the 649. And Namir, I think if you work it out, it ends up being like 1 in 8 million, 1 in 32 million, something along these lines, right? But again, you know what the chances are. in the 649, right, there's 49 numbers. You have to get all 6 of them to win the jackpot. So there's 49, choose 6 possible outcomes, and there's only one way of getting all 6 of them right. So the answer is 1 in, yeah. So the answer for 649 is 1 over 49, choose 6. And in the case of Lotto Max, I guess, yeah, if you're choosing 7 numbers from what? What's the pool? How many numbers are there that you choose 7 from? Because there's more number. Yeah, there's more numbers in Lotto Max, I think, right? Anyway, probability of winning the 649 is 1 divided by 49, choose 6. The way that this is described is basically as follows. Take all the railroad tracks in Quebec and Ontario, right? And for those of you who know, Quebec and Ontario are big places. There's lots of railway tracks. The probability of you winning the Lotto 649 is the same as you determining, like, somebody on those railroad tracks somewhere put a baseball. And your probability of winning the 649 is the same as you guessing where on the tracks the baseball is. Right? And when people are like, those are your odds of winning the Lotto 649, you're like, oh, well, maybe those aren't very good odds, right? Because numbers become very numbing very, very quickly. People don't understand that there's a big difference between 1 in a million and 1 in a billion, for example, right? Mm-hmm. Yeah, there you go. So yeah, people don't understand that like 1 in 6 million or whatever is, or 1 in 5.3 million is like a really small number. And yeah, that doesn't, those seem, yeah, 1 in 33 million does seem too low for Lotto Max. But yeah, so the odds are low, right? And that's what a lot of people don't realize is how bad the odds actually are, because again, the difference in your brain between 1 in 50 million and 1 in 500 million, there's actually a big difference, but to your brain, they're basically both 0. And sometimes we need like a little bit of descriptive statistics to show what's going on there and how unlikely these things are. All right, so the class said B, majority, and phenomenal. That's exactly what it is. That is the correct answer. The correct answer is B. So remember, how do we do that? How do we get that? So the expected value is always the output of the random variable multiplied by the probability that that random variable happens, right? So in this case, we're asked to determine what our winnings are, right? So the random variable is, let's call our random variable X. So let X be our winnings. And again, we can only win money, right? We can't lose money. We could break even if we don't get any of the numbers right. But we can't lose money because we didn't pay anything to play this game. So it's the best kind of game in the world, right? So X is our winnings. And so we know that if we get, let's call it X of X of N for how many numbers we get right, okay? So if we get 0 numbers right, we win $0. We get $100 if N is equal to 1, we get $200 if N is equal to 2, and we get $300 if N is equal to 3, right? Okay, and actually it occurs to me, I just want to pull up my notes and just make sure that I'm using the same formula in my brain that I gave you in the notes, because I don't want to confuse anyone if I write this out. Right, okay. So the expected value of X is equal to, and I know it's sigma notation again, right? Where R is the possible, is the range of your expected value, i.e. it's the set of possible outcomes. So in our case, so for us, if we write this out, this is going to be the expected value of X is going to be 0 times the probability that X equals 0 plus 100 times the probability that X equals 100 plus 200 times the probability that X equals 200 plus 300 times the probability that X equals 300. Now, a lot of time when you're doing expected value, it's not necessary to write this equation out. And I know that some students do tend to go straight to the final answer. You want to be a little bit careful when you're doing that because one, a lot of students get burned for this, especially when we're doing things like winnings and losings. and they're not careful about this. And two, again, your goal is just to demonstrate that you understand what you're talking about. Writing out such an equation is a really good way of doing it, right? Okay, so what we need to do is compute the probability of each of these outcomes, right? Now, in practice, we don't care what the probability that x equals 0, we don't care what that probability is, right? Because we're going to multiply it by 0. So this, we don't care, right? Because we're going to multiply it by 0. Sure, Emma, yeah, I assumed you just typed something by accident. Okay, so we need to determine the probability that x is equal to 100, right? That's the same thing as saying, what's the probability that I win $100? So the probability that I win $100 is the same as the probability of getting one number correct, okay? So what is the probability? First of all, what is the total number of ways that I can choose 3 numbers from 49? 49 choose 3, perfect. All right, so you've got 49 numbers, you're going to choose 3 of them. I don't know if this is clear in the question. I guess it's not, but in the lottery, you don't care about the order of the numbers, right? The only thing that matters is the numbers themselves. So that's why it's choose and not, that's why it's C and not P, okay? Now, how many ways are there of you correctly choosing the correct number? Let's say, again, you're only going to choose one number, right? So how many ways are there of you correctly determining your one correct number? Yeah, exactly. 3 choose 1, right? Because there are those 3 numbers there, and you're saying, it's one of these 3, right? So there are 3 options there. And then the other 2 numbers, exactly, there's 2 numbers left over. There's 46 other numbers other than the ones that you chose, right? So you chose 3 numbers. One of them is correct. There's 46 numbers left over that you didn't choose, and you need to pick 2 of them. So 46 choose 2. And this is multiplication. Let me just maybe put a little X there so we remember that. So does that make sense? Right, I chose 3 numbers. There's 46 left over. One of my numbers was correct. So there's 3 possible ways that it could have been one of my numbers. And then there's 46 choose 2 other ways of choosing the other 2 numbers. Okay, let's do, and please let me know if that didn't make sense. What's the probability that x is equal to 200? Well, that's the same. Why not just 49 instead of 49 choose 3? So I'm not certain why it's 49. 49 is the number of ways of just choosing the first number, right? And we need to choose 3 numbers for all the possible ways to pick 3 numbers out of a hat, right? So you've got a big bin with balls, and each ball has 3 numbers on it, and you're going to reach your hand into that bin, you're going to pull out one. Well, there are 49 things you could have chosen for the first one, but you also could have chosen, right? You also get to choose a second and a third, but then you also don't care about the order of those things, right? Okay, so let's do an example here. Okay, so let's say I chose the numbers 3, 18, and I don't know, 45, okay? And what I want to figure out is all the number of ways that one of these numbers appears out of the 3 that were chosen, but exactly one of these numbers, right? So what are all the ways that I could choose 3 and 2 other numbers? Well, that's 46 choose 2 are the other 2 numbers, right? And then I would have to do 18 and 46 choose 2, and then 45 and 46 choose 2. Okay, so does that make sense? And okay, hold on, let me just read everything. There are 3 connect numbers, so you can choose 1 correct and then at least 46 numbers. Yeah, Josefa, I think that's a totally fine way of thinking about it as well. We know that there are like multiple different perspectives and paradigms that you can have when you do these problems. I think that's a totally fine way of doing it. And yeah, you can do it that way as well, and it should give you the same answer. You remove the 3 correct numbers out of the 49 numbers and choose 2 so that only 1 is correct. That's why it's 46, choose 2. Okay, is everyone okay? Did we answer that question well enough? Everyone's happy? Okay, so the probability that I get 2 numbers correct, again, the way I'm kind of thinking about it is I've got 3 numbers and 2 of my numbers are going to show up, right? So if I've got 3 numbers and I need 2 of them to show up, how many ways are there of doing that? 3 choose 2, exactly. Okay, and then there's one number that I didn't choose. So how many ways are there of choosing that last remaining number? 46 choose one, or just 46, but yeah, 46 choose one, those are the same thing. And then again, divided by 49 choose three, right? And you can see what the pattern is. So finally, when x is equal to 300, there's like basically it's just 1 out of 49 choose three, right? I think in the problem we wrote it as 3 choose 3 times 46 choose 0, but both of those numbers are just 1, right? No, okay, so now what we're going to do is we're going to plug these into this formula, right? So we're not going to multiply them, but we're going to plug them into this formula. And so when I do that, I get 100 times, 3 choose 1. I'm being bad with my subscripts here. 3 choose 1, 46 choose 2, divided by 49 choose 3, plus 200, 3 choose 2, 46 choose 1, divided by 49 choose 3, plus 300. And again, the way we wrote this, again, this numerator is just 1 here, but it kind of gives you an idea for how it works. So let's keep it that way. And then you can figure out what that number is. And we did it for you. It's $18.30. Right. And again, in practice, if you were actually doing the lottery, you would, you're not giving tickets away for free. You would set your ticket price to be greater than $20 in this case, right? Just to ensure that, you were making money, right? Because that's your goal as a corporation, right? You want to make money. So you'd set your ticket price greater than this number. Okay, does that make sense? And there's a bunch of good examples of doing expected value. You should definitely try some of them from the book. Let me see if I can't find one. I love the ones where we play games and one of us cheats. The sigma thing is a formula? Yes, absolutely. So the sigma thing in our case became this. For us, if we were to expand that sigma, it became this formula. Okay, and so everyone, the expected value is nothing more than a weighted average, right? That's what it is. It's saying you're taking the average, but depending on the outcome, you're weighting it slightly differently. So that's all the expected value is a weighted average. Okay, everyone's good? Why does the E, that's my sigma. This is my, I guess it's hard to draw good Greek letters. Maybe the sigma is a little bit cleaner. What is it? It's like this, right? But that's my capital sigma. On the left, oh, that's, I see. So the question wasn't the sigma, it was this one. And that's just I don't know. We just use this for notation. I don't think everyone does, but a lot of people do use this blackboard bold. You know how like when we write the real numbers like this, or the integers like this, or the rational numbers like this, it's the same font, right? It's our blackboard bold, and it's just to distinguish it as being, something special that is often referred to. So it's just the same font as those things. Yeah. It's nothing special. Some people just write E. And if you just want to write E, in this context, it's totally fine. Like I wouldn't worry about trying to, replicate that exact notation. You can just say the expected value is E of X and just write it as, E of X. And same thing, we often use square brackets. If you use like parentheses, it's not the end of the world, right? No one will be upset by that. But most people use square brackets, and most people do use the blackboard bold E. Okay. Okay, cool. All right. So that's going to finish it for our lecture today. We're going to go into office hours now. Maybe just give me a couple of seconds here, a minute or two. Aziz, are you going to take off soon?
I'll probably hang around for a bit.
Okay, cool. So everyone just give me a minute or two and I'll be right back.
I'll hang around and answer questions as well. Meanwhile. Yeah, I agree. I feel like this lecture always goes by very quickly. It's exactly that. Are you guys referring to like when you say management, are you guys referring to like MGM 101? Or MGT as an MGT 120, like accounting? Accounting. The thing is, accounting is one of these weird ones. Like accounting for me is like a relatively drier subject in general overall. But for the people I know that really like accounting, for them they always love those courses. But for the people that don't like accounting, it gets really dull. Because I think, I don't know, accounting is one of those ones. You either love it or you hate it. You'd say so. Accounting in person, even, by the way, it can get very dull if you do it for a long period of time. Who's the best prof for MGT? I don't know who the profs are anymore. I think when I took the course back in the day, some of the profs I don't think they're still here. So not sure.
I love how the chat has just evolved into
if anything, they're saying they enjoyed this lecture versus some of the other lectures.
I mean, that's great. Yeah, that's what I want to hear. Like, you know, I can't imagine many of you ever thought you would enjoy math class. So I figure, you know, we must be doing something right. All right, so I've got a request here, 421C, 422D, and E from the PDF. So maybe let me pull those up and let's see. Ooh, this is a nice one. I like this. Good choice. Yeah, I mean, you know, the reality is math doesn't have to suck. It's just that, you know, so often it's taught in kind of a crappy way. And the reality is, I think math is actually even more fun than this class. But, you know, I can't show you the really fun stuff. Because then management and econ would be like, what are you doing, man? Okay, so let me just set up the problem. So this is 421, and if you don't want to pull it up, I'll sketch it out. I won't write out the whole problem in exactly, but you're told the blue die is fair and the red die does the following. So red die has the probability distribution. I'm going to write it like this, which is just a little bit different than how it's done in the notes, but it's the same thing. So 1/9 if X is even, and 2/9 if X is odd, right? Okay, so it's not a fair die, right? It definitely does some non-good things. Okay, yeah, it's probably true, Joseph. I think I was in a, thanks, Brandon. If we have time, can we do number 5 in that doc? Okay, so Curdy, I assume the one you sent to me. Explain combining events. Okay, sure. So hold on, let me just kind of take some notes here. Okay, it was given to you in the question name. So it just says, you know, 1/9, you're told that your red dice is unfair. and that it comes up an even number, a ninth of the time and 2/9 of the time it's odd. Yeah, okay, no problem. So I think I was only asked to do C, but we might, let me just look at it and see if we need to do the other ones first. Okay, write out E and F. So E is the event one die is exactly twice the other. One die is 2 times the other die. And F is both die are a multiple of 3. So yeah, I think we're not going to be able to just go straight to C here. We're going to have to kind of do both of them. Explain sample spaces or an example. Sure. So yeah, I mean, this is actually a good time. We could talk about sample spaces now. So we roll both die. The sample space is the collection of all possible outcomes, right? So this is kind of a direct message asking me to kind of explain sample spaces, and we've got a good question here, so I might as well explain it here. The sample space for this question is the collection of all possible outcomes, right? So we can usually we write these down sort of in a chart when we do dice, but you don't have to. But, we'll often write like the sample space is, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. I'm not going to write down all 36 of them. But, it goes on like this, right? 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Right? So the sample space is just the collection of all possible outcomes of your experiment. So we said we're going to roll 2 dice. What are all the possible outcomes? Oh, the first die is one number and the second die is another one. And in this case, that gives us 36 possible outcomes. Okay, so does that make sense? That's just what the sample space is all possible outcomes. Okay, cool. So in this case, let's be careful. I should say which number is which, right? So let's do the blue die is the first number. So let's do the blue die is the first number and the red die is the second number. Okay, it doesn't matter which one you do, but make sure in a test you tell us which one is which, right? If you're going to write this like this, and especially when they're not fair, make sure that you indicate in the tuple which is the blue die and which is the red die. Okay, so let's write out the event E. Okay, so the event E is one die is exactly twice as much as the other. Okay, so let's start writing this out. So what do you guys think? So E is what? Give me some of the things in here. Okay, 2, 4. I mean, Brandon, I don't know why you're starting in the middle, but sure, 2, 4 is definitely an option. 2, 4. And while we're at it, okay, let me flip the ones that you give me. Okay, so 1, 2, somebody gave me, and I'm going to flip that as well and do 2, 1. A 3, 6, and 6, 3. Yep, 3, 6, 6, 3. Okay, do we have anything else? Is that everything? What is E? Oh, E was one die is exactly twice the other. Is 2 times the other. Does that fix it? You get what we're doing now? Okay. So that's all of them, right? I don't think there are any more because we can't be bigger than 6. So we can't have like 4, 8. That's not possible. We can't be less than 1. So I think that's it. Does everyone agree? Okay, cool. So E displays what is needed in the question. Yeah, right. In the question, it says what E is. It says that E is one dice is exactly twice the other. Okay, now F is both dice are a multiple. For some reason, I guess I didn't finish this question or this statement. Both dice are a multiple of 3. Okay, so let's write out F. Okay, so start giving me the options for this one. So both have to be a multiple of 3. 3, 3 is in there. 3, 6, 6, 6. Yep. 3, 6, 6, 6, and 6, 3. Exactly. Thank you. Great. And that's everything, right? Because the only multiples of 3 that can occur on a dice or on a die are 3 and 6, right? So it's just there are 2 options for the first die, 2 options for the second die. That's all it could be. So there's 4 options. Okay, so that's part A. Part B is, are these mutually exclusive? So somebody tell me, are these mutually exclusive? Okay, no, why not? So multiple means like 3, 6, 9, 12, 15, 18, 21, 24, right? Like it's all a multiple of 3 is 3 times k for some number k. Yeah. Yeah, 3, 6 is in both sets, absolutely. And I think 6, 3 is also in both sets, right? Exactly. So we get E intersect F, right? So we're looking at what numbers are in both sets. And it looks like these are in both sets. So this intersection is 3, 6, comma 6, 3. And for them to be mutually exclusive, this has to be empty, right? There can't be any intersection whatsoever. So these are not mutually exclusive. For the record, I also think this was a term test question one year. Okay, so that was B. All right, so for C, determine the probability of E and the probability of F. No, so remember, so Curdy, an interesting definition of a set is that there can't be any repetition. So the same thing can't appear in a set twice. So in the intersection, it's just those two numbers. Even though they do appear in both sets, in a set, you can't have repeated things. Yeah. Okay, so C, determine the probability of E. Okay, so the probability of E, what's up here? So we're going to get, we want the probability of 1, 2 plus probability of 2, 1 plus the probability of 2, 4. There's a faster way of doing this, but I really just want to spell out what exactly it is that we're doing. 3, 6, and 6, 3 plus the probability of 3, 6 plus the probability of 6, 3. Okay, is everyone okay with that? Right, like that's how we compute the probability of an event, is we determine the probability of everything in the event and then add them all together. Right, and normally we don't have to worry about that if everything is fair. But in this case, we have a loaded die. So we need to be careful and make sure that we do this the proper way. Okay? Everyone's okay? Okay, so let's do the probability of 1, 2. Okay, so remember the first die, this is the blue is first, and the red is second. Now these events are independent, right? The outcome of the first die does not affect the second die and vice versa. So I can just compute this by saying, this is the probability that the blue die is 1 times the probability that the red die is 2. And what is that? So what's the probability that the blue die is 1? 1/6, right? Because it's a fair die, right? We said the blue die is fair, exactly. Okay, now what's the probability that the red die is 2? 1/9, exactly, right? And here's where we differ from being fair, because all of a sudden this weird number comes out and it's 1/54. Okay, now it says that in the table that's right above. Yeah, exactly. Yeah, that's what's way up here, right? Yeah, why is it 1/9? Is because right here. Yeah. Okay. Now, let's not do this for all 6 numbers. I think that we recognize that kind of the interesting thing that's going to happen here is this is also the same thing as the probability of 2, 4. That's the same thing as the probability of 4, 2. And it's the probability of 3, 6, right? Because the only thing that's interesting, so for each instance, the probability is either 1/54 or 2/54. Right, exactly. So all we need to do, and as Brandon points out, the only thing that matters is whether the second number is even or odd. Does everyone agree? Because the first number is always a 6. The blue die is always fair. So that number is always going to be 1/6. So the only thing that matters is the second number. And if it's even, it's going to be 1/9. And if it's odd, it's going to be 2/9, right? So I said that these are all equal because their second number is all odd. Now, if you were to write this in a test, what you would say is, before you wrote down this line, you would say the probability only depends on whether the red die is even or odd, right? And so here are all the ones where the red die is even. So all of these are equal. They're just all equal to 1/54. And then we just need to worry about when the red die is odd. So how many cases did we take care of? 1, 2, 3, 4 here. And there were 6 cases, so there should be 2 left over. So that's going to be the probability of 2, 1, which is going to be the same as the probability of 6, 3. And did I get the, is that, let me just double check here, because I feel like 2, 4, 4, 2, 6, 3. Yes, those are the only 2 cases, right? And that's going to give me 1/6 times 2/9 is equal to 2/54. Okay, everyone agrees? Are there any questions there so far? And so, and if you're typing, just keep typing. So what I would say in this case is that instead of adding them up, I'd say there's 6 events at 1/54, or sorry, it's not 6. There's 4 events at 1/54 and 2 events at 2/54. So if we add them up, what are we going to get? 4 plus 4, so that's 8/54, which is, I guess we could do that as 4/27 if we really wanted to. Okay, and then you do the exact same thing for F. That's just the first part of C. So C says compute the probability of E and compute the probability of F. So that's all that we do there is, so that's the probability of E. We'd still need to do the probability of F though, right? Now, one of you, I'm sorry, I don't remember who, asked me a side question here. So before I move on about combining events. So whoever asked that, can you be more specific? Because now would be a good time because we've got these 2 events here. So this would be a cool time. Wait, so if red is even, then the probability is 1/9. Yes. Right? The red die, we said the probability of the red die is 1/9 if X is an even number and is 2/9 if X is an odd number. And Brandon, exactly. And like, it's always going to be 1/54 or 2/54. Like every single thing in the sample space will have one of those probabilities. And it just depends on whether the second number is even or odd. Just the concept of combining probability in general. So I mean, like, it kind of depends on what you mean. Do you mean like combining sets and then computing their probability? Because one thing we could do here is, we could do, okay, sure. Yeah, find a textbook question because that will be useful. Did the problem say that the first die was blue and the second die was red? It doesn't, the problem doesn't specify. That's just what we chose to do. And same sort of thing in a test, you can choose which one is blue and which one is red. But again, you need to make sure that you say which is which, right? If it doesn't tell you which is which, you get to choose it, but you need to say which one is which. Because you imagine if you're a TA and half the class chooses one way and half the class chooses another way, you just don't know what's going on. And you're going to get angry, right? And you're just going to be like, no, you didn't tell me what you're doing. I can't read it anymore. And you won't get a good grade. So just make sure that you say what you're doing, right? Oh, okay, sure. Yeah, so here's kind of a thing that was brought up too, like the probability of the complement of E is 1 minus the probability of E, right? And it just says, okay, so now let's say, so E complement, so again, remember for E is the event 1, or maybe let's do, yeah, here, let's do F, okay? So remember F is both dice are a multiple of 3, right? So the complement of F is the negation of that sentence. Yeah, so let's do an example. So what if I said, what is F complement? You might do something like, well, neither die, or one of the die is not a multiple of 3. Okay, and I could say, compute the probability of the complement of F, right? No, you want or, right? Because the complement, like the negation of an and is an or. right? If I say both dice have to be a multiple of 3, the negation of that sentence is one of the dice is not a multiple of 3. Right? Yeah, because for example, this would be an FC, right? Both die are not a multiple of 3, but one of them is. So it's important that we say only one of them has to not be a multiple of 3. Okay, so what if I said compute the probability that one of the dice is not a multiple of 3? And so if you were to write out this event has what, 32 things in it? There are 32 of these, right? That's a lot. That's kind of messy. Like you probably don't want to do 32 computations. It's actually, again, as Brandon says, everything's equal to 1/54 or 2/54. So really you just need to compute how many are of each type, but you don't want to do that, right? So what we would do is we'd say, okay, well, the probability of the complement of F is the same thing as 1, right? 1 here means 100%. Minus the probability of F, right? And we can compute the probability of F because there's only 4 things in the probability of F. Right, and then this is, so what is it? If it's even, it's 1/9. So this is, no, this one's 2/54. Plus 1/54 plus 2/54 plus 1/54, which gives us what, 6/54? So therefore the probability of the complement is 1 minus 6/54. So that's what, 48/54? So does that make sense? Like that's how we'd use that formula. No problem, Jack. See you later. Yeah, I mean, does that make sense though? Like, do you get it? Like sometimes computing the event that you want is really messy. And in that case, it's often, okay, yeah. So, right. And when would you use this? It's, remember here we said F complement had 32 things in it and F had 4 things in it. So if I ask you to compute something that has 32 things in it, you might be like, oh, that's gross. Why don't I compute its complement instead and then just do 1 minus that, right? See ya, Davin. So that's how you determine which one to do. Now, if both F and its complement had, say, 16 things, there's probably no value in using the complement. But generally, look at an event, look at its complement, try and decide which of these things is easier to compute the probability of, compute it, and then if you need to switch back to the complement, you can just take 1 minus that probability. Okay, so the question is, I got a direct message, why is it 2/54 for P33? So assuming I didn't mess it up. So this is the probability that the blue die is 3 times the probability that the red die is 3. But the blue die is fair, so the probability of anything is 1/6. And the red die is 1/9. 2/9. Right? So that's 2/54. Actually, 2 of you messaged me that at the same time. Okay, so other direct messenger. Okay, cool. Yeah, it's that thing that like, actually, I feel like, we didn't do 3/3. But yeah, so again, remember the probability of every single pair is either 1/54 or 2/54. Like this is always true. So the probability of NM is equal to 1/54 if M is even, and 2/54 if M is odd. Right? This is what Brandon has been saying in the chat, right? That the only thing that matters is the second number. All right, see you, Ahmed. Okay, so hopefully that clarified a few things. Now for, what was the other one? 422, D and E. Oh man. Okay, so 420, so there's this, okay, you guys are gonna have to pull up 422 because there's a big chart there that I don't want to fill in. So 422 is if the two students are chosen at random, what is the probability that they both like the same music? Okay, so this is going to be law of total probability, right? What's the probability they both like rock, plus what's the probability that they both like pop, plus the probability they both like hip hop, plus the probability they both like Estonian folk metal. So the probability that they both like same music equals the probability that they both like rock, right? Plus the probability that they both like pop, plus the probability they both, and so on and so forth, right? I'm going to start getting lazy and not write the word like. Okay, so let's look at the probability that they both like rock. Okay, and I think that once we do this one, we'll kind of see how to do the rest. So the probability that they both like rock. Okay, so if you choose a student at random, what's the probability they choose? What's the probability the first student likes rock? Maybe not everyone can see the table. Actually, I guess I have to do the addition because I don't know it off the top of my head. Is it? So how many people like rock? So 32, 44, so 46 out of, and how many people are there total? 30, 46, 48, plus 48, plus 30, 41, plus 8. So that's going to be what? 1, 2, 3, 7. So that's 46 over 143. Is that 145? Did I miscount it? Somebody double check my math here. Somebody pull up a calculator.
That's good.
Is it 143? Because Ariana says it might be 145. It's 143? Okay, sure. Okay. So it's, and the number of people who like rock is 46, right? So 22, 32, 44, 46. Yeah, or Ariana, no worries. Like, it's, we all make those little mistakes all the time. You've all seen me, add numbers incorrectly. So that's the probability that the first person likes rock, right? And then what we need to do. Now, what's the probability that the second chosen person likes rock as well? Okay, but that assumes that you can choose the same person twice. Right, 45 times 142. Right? Because once you chose the first student, you take them out of the pool. You don't choose the same student twice. So now there's 142 people in the pool. 45 of them are left over that like rock because you've already removed one from both cases. And this is the probability that they both like rock, right? And then you just do this for pop, do it for hip hop, do it for Estonian folk metal, and then add them all up. And that's how you do that's how you do D. Okay, so does that make sense? I don't remember who originally asked. Actually, I think it was you, Christian, who asked that. Like, does that make sense to what I did there and how to do it? Okay, cool. Okay, yeah, let me look at 423 in a second now. Very quickly though, I think I was asked to do E on this one already. So E is if two students are chosen at random, what's the probability that they both like hockey or one of them likes Estonian folk metal? So the probability that they both like hockey is the same way, right? Okay, so hockey is 20, 42, 44. So 44 over 143 times 43 over 142. The probability that one of them likes Estonian folk metal we're just going to call it EFM, is what? Okay, it's going to be the probability that the first one likes Estonian folk metal plus the probability that the second one likes Estonian folk metal minus the probability that they both do, right? So this is going to be 2, 4. So this is going to be 16 over 143 minus 4 times 3 divided by 143 times 142. 46 choose 2. Okay, so Ariana, that's an interesting way of doing it. What you've done though, what you've computed is, does that work out? I think it does. I think mathematically that's the same thing, but let's just double check it. Okay, let's just make sure. So 46 choose 2 is 46 factorial divided by what, 44 factorial 2 factorial, and then you divided it by 143 choose 2. So that's 143 factorial divided by 141 factorial 2 factorial. Yeah, it does give you the same number. So this is 46 times 45 divided by 2 divided by 143 times 142 divided by 2. The 2's cancel, and that gives us 46 times 45 divided by 143 times 142. So it's the same answer, Ariana. Yep, so that's exactly right. So why did I do both? Okay, yeah, and Jeremiah has asked the same question. So the probability that the first, that one of them likes it, likes EFM, equals the probability, how do I want to say this? It's the probability that the first student likes it plus the probability that the second student likes it, but I've double counted, right? Because in both of these cases, I've double counted where both students like it. Oh, I guess it should be 8 times 7. Maybe that's what the issue was, is that I wrote the wrong numbers down. Does that make sense? So it shouldn't be 4 times 3. That was my mistake. It should be 8 times 7. Jeremiah, you're good too? Or, okay, cool. And then once you have both of these, you add them up, right? And you're good. Though I guess you'd also have to subtract, no, those are independent, right? Like whether or not they like hockey or Estonian folk metal, I think are independent events. Yeah, okay. So 143, Lenny jumping hurdles, probability that jumps both hurdles 75%, with the probability jumps the first hurdle is 90%. Having successfully jumped the first hurdle, what is the probability he successfully jumps the second hurdle? So for 423, you know that the probability of both is 0.75. You know that the probability of the first hurdle is 90%. And you want the probability that having successfully, right, so you want the probability that he successfully jumps the second hurdle, given that he successfully has done the first. So that's going to be the probability that he does the first and the second, i.e. the probability that he does both, divided by the probability of the first hurdle, right? Does that make sense, Brandon? Okay. Let me just check here. Did anyone ask anything? So, oh, that Curdy, you asked me about that tutorial question. Why did I use probability first for the bottom? So the probability of E given F, right, is the probability of E intersect F divided by the probability of F. So I want the probability of second given first, so I divide the probability by the probability of the first. Right? First event, F, F. Okay, cool. So how do you read notation again? So like, what do you mean like this? The probability of E given F? Direct message? Yeah, okay. So this is the probability that E occurs given that F has already occurred. Okay, so that line, you can think of it as just saying given, right? The probability of E given F. So it's the probability that E occurs given that F has already occurred. Does that make sense? And then I've got to go up and get that tutorial question, wherever the heck it is. Oh, there it is. And what was the question from this tutorial? 5?
5, I believe.
Okay. How many words can you create of length 6 from the letters A, B, C, D if you must include at least each letter once and A must appear exactly once? Oh my God. Damn it, Paula.
It's a good question.
Yeah. A, B, C, D. Okay, A must appear exactly once, eh? Okay, so what I would do is I would say A is the most restrictive. So we should choose where A goes. Because we know it has to, well, each letter must appear once, but there's 6 letters. Yeah.
Some cases here, right? So you want to look at the because they're so A. Let's assume it's going to happen where we're going to have A, B, C appear one time each exactly, and then D appearing 3 times. So we're going to have a case where a letter gets repeated 3 times and everything else happens exactly once. Or we're going to have the case where two letters get repeated twice and everything appears exactly once.
I think I can do this in one case. So I would say, yeah, I think the answer is 6 choose 4 times 4 squared.
6 choose 4. So you're choosing from the 6 letters, you're choosing A, B, C, D. And then for the remaining 2, you're saying there's 4 options for each, so there's 4 squared.
Oh, wait a second. 6 choose 4 and times 4 factorial.
But times 4 squared, that way you could potentially pick the A again in that case.
Oh, that's true. Damn. But then can I just do 3 squared? Because I'm saying the A is already in there, right? So the only thing left is B, C, and D. So basically what I want to do is I want to say, okay, there's 6 slots, right? So I'm going to choose 4 of them. Oh no, but now I've overcounted.
Yeah, that doesn't work either.
Yeah, I've overcounted. You're right. We have to do it in cases.
I would think so, because you have to do a case where you have to do either like 2 letters appear 1 time each and then 2 letters appear 2 times each,
Yeah.
or the case where 3 letters appear 1 time each and then 1 letter appears 3 times.
Yeah, you're right. We do have to do it that way. Gross. Okay. Yeah, so yeah, you have to break it into cases. All right, case 1 is 1 letter appears 3 times. 3 times. And namely, it has to then be B, C, or D.
Mm-hmm.
So 1 of 3 times, maybe let's just say B, C, D. And then A appears exactly once. Okay, so if this is true, then basically we've got 3 options for the letter that appears 3 times. And then what do we have? So we've got 6 pick 4. Is that how I want to do this? So we've got, like, let's say B, B, B. Let's just write out an example. A, B, 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 C, D, right? That's 6. And you want to know all the ways that you can arrange this. So that would be 6 factorial divided by the repetition, 3 factorial, right?
That's correct.
Okay. So this answer will be 3 times 6 factorial over 3 factorial.
I agree.
Okay. So Jeremiah, this is that tutorial that Curdy posted in the chat a while ago, and is question 5 on that.
Tutorial 10, question 5.
Yeah. Okay. Case 2. So 2 letters appeared twice.
Again from BCD.
Yeah, twice. B, C, D. Okay, so let's just do an example so we can ground ourselves. So we're going to have A, B, B, C, C, D, something like that, right? Okay, so we've got 3 choose 2 ways of choosing which 2 letters repeat.
Mm-hmm.
Choosing the repetition, the repeated letters. And then once we have that, it's going to be 6 factorial divided by 2 factorial ways of arranging those letters. So this case is going to be this number times 3 choose 2.
Mm-hmm.
And those are the only cases, right?
Yeah, that's everything.
So then you just add these.
Yeah, because if you try arranging them like the letters, like just manually try to see if there's anything else, you have to do one of these 2 ways.
Yeah. Thank you. So Curdy, the 6 factorial over 2 factorial is like you've got imagine I asked you exactly this question, right? Which is you've got A, B, B, C, C, D. How many words can you make from this? Well, it's 6 factorial because you have 6 letters. But then remember, you have to divide out by each of the repetitions, right? How many times each letter is repeated. So we have 2 factorial for the B's and 2 factorial for the C's. So that's that choice where I chose B and C were the repeated ones. And then I multiply by 3 choose 2, which is just 3, for how many ways that I could choose which letters were repeated, either B or C or A or C, or what did I miss? A and B.
You can't do A can't be repeated. B, C, C,
Oh, yeah,
D,
yeah, that's true. Yeah,
D.
D. Yeah, thank you. Can you not do 2 factorial squared? Yep, that's the same thing. Can case 1 also be like 6 factorial over 2 factorial? Yep, absolutely. And in that case, we know that this is 6 factorial over 2 factorial. And let's see if there's an obvious reason for why that's true. So we could have like A, B, 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 C, D. And so this is the same thing as 6 pick 4, right? So I guess what we could say is I want to choose where A, B, C, and D go. And then the other 2 slots have to be B, B. But then, no, because I still have to choose which were the double slotted. So it is 6 pick 4, but I don't see immediately why if we could go straight to 6 pick 4. I'd have to think about that a little bit. Okay, anything else? Is it P because order matters? Yeah, exactly, because order matters. But I mean, none of my solutions here actually used P. But yeah, can we go straight to 6 pick 4? How would we do this? What would we argue? Is there a perspective where this is obviously this answer? So A has to go somewhere. We're going to choose where it goes. Order does matter. And then B, and then C, and then D. So that is 6 pick 4 slots. But then the last 2 slots aren't forced because you have a choice. I'm not seeing a way to go straight here. Right? The fact that these 2 numbers are equal might just be a coincidence. I'm not seeing a way to go straight to 6 pick 4. Theodora, for which one? For case 1? And well, how did you do it? Because that's the same answer. Right? 3 times 6 factorial over 3 factorial is 6 divided by 2.
I do think it's just happens to be a coincidence, to be honest. I don't think you can do it using 6p4.
Yeah, I don't see an obvious way that that's true.
Because what are you picking 4 from in this case? Like, what are the 4 things you're picking? Are you picking the 3 repeated and then this? I think it's more of a just happen, like, because the numbers worked out more than anything else.
Yeah, but it doesn't mean it doesn't exist. It just means we don't see it, right? Like we could be saying, yeah, I don't see it, because the problem is that you need to be able to say which of the letters you're repeated, right? And I don't see how you're going to build that into just the straight 6 pick 4. But Theodora, please write up what you did, because maybe you did see something we didn't see. Just because I don't see it doesn't mean it's not true. So if you do have a solution, please write it up, because maybe you see something I don't. That's totally a possibility. Every now and then we're definitely surprised that a student thinks of a question in a way that we've never thought about it before. And we're like, oh, hey, that's a cool way of thinking about it. We didn't think about it like that. So it totally happens. It happens every year. Yeah, and I don't think we can get straight here. I don't see an obvious way.
I'm thinking about it as well. I don't see a way right off the bat that hits me here that makes it work. But there might, as you said, there might be something that we're not catching here.
Yeah, we could do it if there were 2 other letters that could be repeated as much as they wanted. But the fact that, right, we're definitely going to overcount if we do it the first way I suggested.
Mm-hmm.
Okay, yeah, that's a nice question. In that it's not too bad. It definitely has some cases, but yeah, it's not terrible. Thank goodness Aziz was here to tell me what to do, because I would have thought I had to think about it a little bit more. So thank you, Aziz.
Honestly, it helps. I did this question last week as well, so still fresh in my mind. I'm just curious. I actually want to do the math, see how, like, if you did overcount in your solution, like, is your number a lot higher than the current solution right now?
I think it is. So what did I say originally? So I said it was going to be 6 pick 4 for the original 4 locations, then 4 factorial to mix them up, and then 3 squared. Right. And the problem with this is, so let's say let's say I'm boring and I just choose the first 4 slots for A, B, C, and D, and I put them in this order.
Yeah.
And then my next 2 letters are B and C. This is the same thing as if I had done A, B, C, D, and then chosen B and C here. Right? So what I'm saying is this is 1, 2, 3, 4, and then I chose B and C as 5 and 6. That's the same thing as if I had done 1, 2, 3, 4, and then chosen this as 5 and 6. So I've overcounted there. So what I would need to do is say, okay, I've overcounted now, and then again, I have to go into cases no matter what. So in the event that the same letter was repeated 3 times, I need to, how many times did I overcount that? So I would need to do something like divided by 3 factorial for where the same letter occurs 3 times, right? Because here the B is 3 times. And I think I treated them as kind of separately. So I think I'd need to divide by 3 factorial to get this one out. And then where the 2 letters are repeated twice, I think I would need to add that exclusion, but I'm not even certain that these are divisible.
I don't think you could do that though.
Yeah, I don't think so either. And you have to break it into cases either way. So it's definitely not like worth doing it that way.
Yeah, no. Interesting.
Yeah, and like how different are these numbers? So
I mean, this is 6. This is 6 pick 4 right there times 3. So that's just case 1. It's pretty much.
yeah. So this is 6 times 5 times 4 times 3. So this is 30 times 12. So this is 360.
Yeah, times 3.
I don't know. I already did the 3 because I canceled these 3s.
Oh, I thought we did that. Okay.
Sorry. Yeah. And then this one, so 3 choose 2 is just 3. And then here I've got 6 factorial divided by 2 factorial, which we already had above. So that's 360 divided by 2. So this is 180. So this is what, 540 plus 360. So the answer is 900.
Yep.
Okay. And then this one, 4 factorial is 24. 6 pick 4 is 15. And times 2 squared is 9.
6 pick 4 isn't 6 pick 4 just 6 factorial over 2 factorial, which is a lot more than 15?
No, it's 6. Oh, it is 6 pick 4. Yeah, you're right.
It's
so no, yeah, we did that. Yeah, what was it? 360?
360 times 9.
Yeah, so we can see it's way bigger, right?
Yeah, it's a lot bigger. How much is it exactly? Let me just do the quick multiplication here. I just want to see if it's off by a specific factor, then we can potentially.
Yeah.
It's 77,760.
77,760.
Yeah.
Divided by 9. Yeah, it doesn't divide 900. Like 900 doesn't divide that.
It's 86.4.
Yeah.
So it's not a nice number.
Yeah, there isn't then an obvious way of doing it.
Yeah, I see it.
Oh, no. Hold on. So if I do 6 pick 4, I shouldn't multiply by 4 factorial, right? Because I've already said that order matters. So I don't need to mix up, right? The original reason why I multiplied by 4 factorial is I said, I've chosen where A, B, C, and D go. And now I need to account for, right? So now it's this. So it's 360 times 9.
360 times 9 is 3,240, which
still not divisible by 900.
It's the 3.6 if you divide by 900.
But at least it's not as far away, right? Like it's a little bit closer.
Yeah, because it's not clearly divisible, I think it makes it like basically like you have to do cases because you can't divide by like a nice number to get the answer. So it must have been like.
Yeah, unless, so what if I do cases again? So I do 6 pick 4 for the A, B, C, and D. And then I say, okay, so they have to, if it's the same number repeated 3 times, that gives me just one option for where it goes. And then if I do the same number, or if I repeat 2 numbers twice, then, so I do 6 pick 4
times
3 times 2.
It'll be B, C, D, and then you have to take one or the other one, but then you have to multiply by 2 again because they can switch position. So would it be 3 times 2?
Yeah.
Because then you can flip them around the 2 letters at the end.
Okay, so then this is 360. Yeah, so this isn't going to work out because this is times 15, right? Damn. So what went wrong here? So I did 3 choices for the third letter and where it could go. Right, but I've still overcounted here. So maybe I need to divide this by 3 factorial. And then I could switch these two, but again, I've overcounted. And okay, yeah, it's not worth doing this way.
The thing is, technically what you are missing for the first case, you're not double counting, I think.
No, I am, because again, it's
yeah, but not by 3
ABC.
factorial, by 3, not 3 factorial, right?
Maybe. Okay, so again, if I do this, is that different than A, B, C, D, 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 and then A, B, C. Oh yeah, maybe it is just 3.
I think it's just 3. I don't think it's 3 factorial.
D, D like this, right?
Yeah.
Yeah, you're right. So I think that's just 3. So this actually just gives us 6 pick 4.
Which is correct. That part is correct for sure.
Okay, and then when we do double, I know. Just give me, yeah. This is just us messing around. And then when I do double, I could have interchanged these two, and I could have interchanged these two. So is this 4 that I overcounted by?
Yeah, you have to divide by 4 here.
So that just cancels out these. So this just gives me 4 times 6 pick 4, which is still too high. Right? That's 1440 or whatever.
5 times 4 times 3 times 4. Yeah, it's 1440. Where are we?
Yeah. Well, we'll get there one day. Anyway, okay. So somebody posted me a direct message. I should answer that one. Yeah, don't worry about it, Theodora. I think we're just messing around to see if we could approach it in a different way. So textbook 414. Oh my goodness, what happened to my note? 414. You've got a bag of 10 marbles. So you've got 10 marbles, of which 6 are red and 4 are blue. You draw 5 marbles from the bag without replacement. How many samples can you draw? Okay, so you've got 10 options for the first one, right? You've got 9 options for the second one, but that one's without replacement. What do I want to do now? Well, oh, it's a dice example. Okay, what's the dice one then? Because in my thing, 414. Oh, it's example 414, not exercise 414. Sorry. Oh, so this is very similar to what we just did, but with the 2/9 thing, right? So consider an experiment. 2 fair 6-sided dice are thrown, their faces are recorded. E is the event that the first die shows an even number, right? So yeah, so we want E is first die is even, and there's 18 of these, right? So we don't want to write them all out. And now in 414, we're told that the probability distribution for the die, for the first die, is 7/12 for x equals 1 and 5/12 for 2, 3, 4, 5, 6. Okay, so the probability that the first die is even is the probability that the first die is 2 plus the probability that the first die is equal to 4 plus the probability that the first die is equal to 6. right?
Mm.
Hold on, let me reread this. So probably the first die is even. Oh, sorry, this is 1/12 because those don't add, that doesn't add to 1. I was like, what? And so this is going to be, I think this should be defense are independent. The second dice is still equiprobable. Let me see if there's a faster way. Yeah, I would just do 1/12 plus 1/12 plus 1/12. Right? That's a quarter. So the example that I give in the solution is like kind of the long way of doing it. But if you recognize that the first and second die are independent, you can just go straight to it. Right? Like you don't care about what the second dice is.
Oh. By the way, actually, yeah, let's finish this. I think I figured out the previous one, by the way. But that's
Okay.
aside.
So what'd you do?
It's just, I think when we divided that one by 4, the second piece by 4, we should have divided by 8. We forgot, like, it could double because we had to switch them around as well. So, yeah. And if you do that, you got the right answer. I double checked already.
Interesting.
So initially there, because we had to multiply by 2, so we divided by.
Yeah.
So we divide by 4, we should divide by 8 and not
Yeah, but
4.
why 8?
No, actually, the way I wrote it the first time, I didn't multiply by 2 twice. Only multiply by 2 in the numerator once, and then I divide by 4.
Right, I see.
That's what I did. That's how I have my equation.
Okay, yeah, sure. Okay, so Sam, does this make sense? So you can do it the way I did it in the book, which is very similar to what we did with the loaded dice example above, but even easier is the rolling of the die is actually independent. So when it says what's the probability the first die is even, you can actually completely and totally ignore the second die and just add up the probabilities.
Oh yeah, sir. So I actually have a question regarding the x equals 1. What does that exactly mean here?
Sure. Okay, so what this is doing is telling you the probability of the outcome. So when we say like the probability of a 1 is what's the probability that a 1 is rolled, right? And then this is like what's the probability that a 3 is rolled, right? So P is telling you what the probability of the outcome is.
Oh, okay, yeah, that makes sense. Thank you.
Yeah, no problem. And so in a fair dice, they're all just 1/6, right? It would just be the probability of X is 1/6 for all X. Okay, everyone, I think that does it for us. It's 7 o'clock now. No problem. Yeah, Brandon, I get it too. Combinatorics is definitely tough. We all think it is. But yeah, so I'm going to take off now. I want to get a little bit of break in and a little bit of food in me before I have to like do my super crunch. Is calc easier? It depends. I think some people will definitely find it easier. Some people will find it harder. It just kind of depends on who you are and like how you think. But I think as a general rule, yes. I think as a general rule, calculus is probably easier.
I would agree.
It's a bit more formulaic, right? It's a bit more algorithmic like that. Yeah, well, hey, 24 hours and you don't have to worry about this at all.
Maybe
right?
that depends on test 4.
That's right. That is true. Test 4 and the final exam. Okay, everyone. Yeah, okay. I'm going to take off. See you. Good luck. And hey, listen, some of you are going to come to lecture on Tuesday. Some of you aren't. So if I don't see you again until January, good luck on your final exams. Have a good break, and I will see you on the other side of December. Okay?
Good luck, everyone.
Bye, everyone.
See you.